That Einstein guy was a real bummer for our hopes of a star-hopping, science fiction-y future. His whole nothing travels faster than light rule seems to ensure that exploration of even the local part of our galaxy will be an excruciating slow. But Einstein also gave us a glimmer of hope. He showed us that space and time can be warped, and so the warp drive was conceived. Just recently, a couple of papers contend that this is not pure science fiction. In 1915, Albert Einstein's general theory of relativity revealed that the fabric of space and time is mutable and dynamic. It can, in fact, be warped. You can't travel through space at faster than the speed of light, but there's no speed limit for the fabric of space itself. This hints at a possibility for faster than light, or superluminal travel. And only 15 years after general relativity's debut, the warp drive was invented, propelling humanity on its first journeys to the stars. That invention, and those journeys were in the 1931 spring edition of Amazing Stories. In Islands of Space, its author John Campbell talks about increasing the cosmic speed limit by curving the fabric of space. The idea caught on. According to the wonderful historical dictionary of science fiction, the first mention of a space warp as a propulsion mechanism was in J. Williamson's 1936 story The Cometeers. Space warp drives, time warp drives, and eventually just warp drives became an increasingly popular way of breaking Einstein's rules. The pretend technology really took off with Star Trek in the 60s, and Star Trek inspired the very first real warp field solution to the Einstein field equations. That's the Alcubierre warp field derived by Mexican physicist and Star Trek aficionado Miguel Alcubierre. Now, we covered Alcubierre's idea 5 years ago. Back then the warp field solution looked like a very rigorous, carefully calculated work of pure fiction. It broke the laws of physics in ways that I'll come back to. Subsequent studies have tried to fix this. And a very recent paper claims to have solved the worst deal-breaker in Alcubierre's proposal. Today we're going to pull them apart, 2 new papers on warp drives, and see if it's really time to don our Star Trek cosplay and warp out of here. Before we get to the new work, let's talk light speed and warp drives. Einstein's speed limit doesn't directly say that nothing can travel faster than light. His special theory of relativity just says that it takes infinite energy to accelerate anything with positive mass all the way to light speed. That effectively means that it's impossible to observe a massive object cross this speed barrier. But there are loopholes. In certain circumstances we can think of space itself as moving, and there's no limit to the relative motion of 2 patches of space, and so objects in those patches could have superluminal speeds relative to each other. For example, inside black holes, where we can think of space as flowing downwards faster than light. Or beyond the cosmic horizon, the expanding universe is carrying galaxies away from us faster than light. The warp drive takes advantage of this loophole by accelerating a patch of space relative to its surroundings. Objects in that warp bubble move with that patch without themselves ever feeling any acceleration. This is what the Alcubierre drive is supposed to do. It's a Einstein geometry that is a valid solution to the equation's general theory of relativity, the Einstein field equation. It includes a comfortable flat region of space surrounded by a region of extreme spatial curvature. The space behind this bubble is expanded, while the space in front is contracted. The resulting push-pull propels the bubble and any spaceship that it contains. The Alcubierre warp field may be a valid solution to the Einstein field equations, but that doesn't mean it's physically possible. Normally, to solve these equations we input a physically possible distribution of mass, energy, on the right side and it spits out the space-time geometry on the left. Alcubierre instead solved the equations backwards. He figured out the geometry of a warp bubble, and then ran it backwards through the equations to see what distribution of matter and energy would be required. You can do this with any geometry, but almost every geometry will produce an impossible mass-energy distribution. To combat this, we have a set of energy conditions that go alongside the Einstein field equations that are meant to restrict the allowable energy distributions to what is physically possible. Alcubierre's field breaks all of these energy conditions, and he's upfront about that fact. We can summarize this by saying that it requires a negative energy density, which should be impossible except perhaps on the tiniest, quantum scales. Sometimes people talk about the drive requiring negative mass, also called exotic matter, and yeah, that would do the trick too, and is also probably impossible. So that sounds like a deal-breaker. The other minor hiccup is that Alcubierre's original field required more energy than is contained in all the matter in the visible universe to move a moderate-sized starship. Subsequent studies improved on Alcubierre's warp design and brought down the energy requirement to less insane levels, although they typically remain somewhat insane. But the requirement of exotic matter didn't go away, and in fact subsequent studies demonstrated that any superluminal warp drive must use negative energy densities. Other studies discovered new problems. For example, warp bubbles are unsteerable because the interior of the bubble is causally disconnected from parts of the front warp field. That inspired Sergei Krasnikov to come up with his Krasnikov tube, a sort of warp conveyor belt, which has the slightly useless property of only working if it's a full return journey and you don't get off at the destination. To me, one of the biggest deal breakers is that any faster-than-light travel can be used to create closed time-like curves, as we discussed previously. That leads to paradoxes, to contradictions and inconsistencies. And the appearance of inconsistencies is one of our most powerful indications that our theoretical musings are on the wrong track. So yeah, warp fields became much better studied, but remained implausible, and probably impossible. But I guess the dreams of wannabe starship captains are strong, because the work continued, and just recently 2 papers have claimed breakthroughs. We'll start with a paper entitled Introducing Physical Warp Drives by Alexei Bobrick and Johnny Martiri. These guys propose a general definition for warp fields not tied to a particular solution to the Einstein field equations. To quote the authors, warp drives are inertially moving shells of positive or negative energy material which enclose a passenger region with a flat metric. Let's focus on that inertially moving part. Bobrick and Martiri is that no past warp solution has inbuilt mode of acceleration. All of them, including alcubires, move with whatever velocity they started at. This isn't exactly a new insight. In 2002, José Naterio demonstrated that the whole expansion and contraction of space was only a side effect of Alcubierre's choice of warp field, and he constructed a warp field without that feature. Naterio, and now Bobrick and Martiri, define warp fields as bubbles that slide through space, potentially at superluminal speeds. But all these guys agree that superluminal bubbles are only possible if the warp field uses exotic matter. Bobrick and Martiri also point out that there's still no way to accelerate a warp bubble across the light speed limit. A superluminal warp bubble has to have started out superluminal. This seems in conflict with Alcubierre himself, who wrote that the warp bubble pushes the spaceship, accelerates it from rest. But this acceleration isn't actually derived from his warp field solution. The velocity of the bubble is baked into the equation for the field geometry, but it's not clear how you change that velocity. This isn't necessarily a complete downer. As pointed out by Francisco Lobo and Matt Visser, if sublight speed or subliminal warp bubbles can be a thing, these might be an example of a reactionless drive, a propulsion method that doesn't need any propellant. Not stuff ejected from behind like in a rocket. But these researchers also note that even a subliminal reactionless warp drive would still require negative energy and an enormous amount of it for any decent-sized spaceship. Okay, let's move on to the second paper by Eric Lentz, Breaking the Warp Barrier, Hyperfast Solitons in Einstein-Maxwell Plasma Theory. This one is a little more Star Trek friendly than, well, pretty much every prior effort. Lentz claims to have found an actual superluminal warp field solution that does not require the impossible negative energy densities. He does this by exploring a broader family of solutions to the Einstein field equations than previous studies. The details are technical, to put it mildly. But let me try to give you a sense of the difference. We can think of the warp field as a special type of isolated wave moving through space, what we call a soliton. In previous work, this wave only waved in the direction of motion. That gave them an axial symmetry. For example, in the Alcubierre field the warp is in front and behind the spaceship, while the exotic matter is in a ring around the direction of motion. When you calculate the total energy with only this component, then it's always negative. Lentz found that by including components of the wave motion that were perpendicular to the direction of motion, he could build a superluminal soliton in which the energy came out positive everywhere. He came up with this example, here projected onto a 2D plane. Energy is distributed along these tracks, potentially as a plasma, in some places at some pretty insane temperatures. This would resulting in expansion and contraction of space in similar regions. The entire patch of spacetime would travel at superluminal speeds, carrying a spaceship with it. A couple of minor issues persist. The energy required to carry a 100-meter diameter bubble is about the rest mass energy of a tenth of our Sun. It's hard to see how packing that much mass into these strips would not create a black hole. Also, Lentz admits that this warp bubble is inertial, just like Bobrick and Martiri assert for Alcubierre's bubble. It can exist at superluminal speeds in theory, but there's no known way to get it to those speeds in the first place. Both of these papers are peer-reviewed and published in the reputable journal Classical and Quantum Gravity. Now, that doesn't mean they're right, it just means that a couple of respectable physicists refereed the works didn't find any gigantic blunders or did, and the blunders were fixed. But much more work is needed to verify anything this speculative. You can bet that there'll be plenty of papers critiquing and/or supporting these efforts. So now you're all up to date with warp technology. Superluminal warp fields exist in theory. And there's a very tentative hint that the worst deal-breaker can be resolved, that of requiring a non-existent type of energy. But other possibly impossible hurdles remain. Can the required energy densities be created without creating black holes for any useful sized warp bubble? And can a warp bubble be created at subluminal speeds and then accelerated past the speed of light? So far there's no known way to do this. And warp fields may suffer the same strict speed limit as does matter. And of course we still have the time travel issue. Accelerating across the speed of light breaks causality and so probably can't be a thing. Einstein and the universe appear to be trolling us, alternately inspiring and crushing our hopes for a star-hopping future. But these studies have made one thing very clear: if warp travel is possible, humanity will figure it out. Scientists are very persistent, especially the ones who are also die-hard science fiction fans. They'll continue to try to make it so. By exploring Einstein's theory, hoping to build Starship, but in the process learning how our universe works. And possibly also building a starship to propel humanity into the galaxy on waves of warp spacetime. Spacetime gets an enormous amount of help from our Patreon supporters. You guys really help us plan ahead to more ambitious episodes and series. And today I want to give a special shout-out to Vinny Falco, who is supporting us at the Big Bang level. Vinny, we've used your support to build a very real warp drive, which, thanks to this new result from Bobrick and Matire, is now possible. These guys define a Type 1 warp field as a surface of positive energy density enclosing a flat metric. Now the authors can correct me if I'm wrong. But I think that this means literally any enclosed surface can make a warp field. Like, for example, a cardboard box could be a warp drive. So introducing the first Type 1 warp drive. We're calling this version the Falco drive. And it's guaranteed to be literally exactly as effective as any warp drive ever constructed. Future versions will be even better. We might add more tubes and some flashing lights, for example. Okay, on to today's comments. We're covering 2 episodes. There's the quantum Zeno effect and the recent result from Fermilab's muon G2 experiment. We'll start with the muon G2 result, which revealed a possible crack in the standard model of particle physics. A few of you asked whether similar experiments could be performed using the tau particle. The tau is the heaviest of the 3 generations of leptons. The probability that a particle will interact with other massive virtual particles is proportional to the square of that particle's own mass. At nearly 17 times the mass of the muon, the tau should be even more sensitive to unknown particles. The problem is that the tau's lifetime is around 10 million times shorter than the muon, which itself lives only for microsecond or so. That makes it pretty hard to watch tau particles precess in magnetic fields, and so far the G-factor for the tau hasn't even been measured to one significant figure. That said, there are other ways to track a particle's interactions with virtual particles. For the tau, the focus is in watching its decay products. For example, the energy distribution of those decay's products are sensitive to the complex interactions with virtual particles that happen during the decay. People aren't really working on this, but you can be sure that there will be even more focus on these experiments going forward. These could yield a truly independent verification of the muon G2 result. Paul Vickery and Verdatum are impressed that Fermilab is producing cutting-edge science even in competition with a much larger Large Hadron Collider. Well, not only has Fermilab remained competitive, it seems to have won the race, or at least it's ahead on the final stretch to find that elusive crack in the standard model that may lead to whatever physics lies beyond. And this is entirely due to Fermilab being extremely clever about where they focus their efforts. When the LHC switched on and Fermilab's Tevatron accelerator was demoted from being the largest in the world, Fermilab made the very hard decision to switch the Tevatron off and direct resources towards things like their neutrino experiments, which we covered previously, and of course the muon G2, neither of which require quite such enormous accelerators. Fermilab's scientists and engineers are right to feel very proud of this result. Okay, on to the quantum Zeno effect and the idea that you can freeze a quantum system by observing it. By the way, the name comes from the Zeno paradox, which argues that a moving arrow isn't moving because it's stationary at each separate instant in time. Ravenlord always thought that the idea of instantaneous velocity that solves this paradox is just a theoretical artifact of calculus. Actually, in quantum mechanics, velocity isn't just change in position with time. Momentum, which incorporates velocity, is as fundamental as position. So a particle at an instant in time really does have an instantaneous velocity. For Flensburg, the quantum Zeno effect reminds them of a poem composed by the Norse god Odin. It goes like this. A fifth spell I know, if I see shot with ill intent, an arrow traveling in a flight. It's incapable of flying too quickly, for me to stop it in its path, as long as I keep my eyes on it. So we can conclude that Odin knew quantum mechanics. I mean, stopping an arrow with the power of observation is a spell they teach you in undergrad quantum. It's also the first midterm exam, which really helps cut down the class size. Also, as everyone knows, Odin plucked out his own eye in order to be able to drink from the mythical well of knowledge. I thought this was just a fable teaching that knowledge requiring sacrifice, but now I see it's an ancient Viking metaphor for the Heisenberg uncertainty principle. By the way, don't think I didn't notice that the last commenter, Ravenlord, bears one of the many names of the Allfather. So maybe Odin learned his quantum mechanics watching spacetime like the rest of us. Alex Turner asks the real question, if the quantum Zeno effect plays a role in birds' ability to see magnetic fields, then according to the many worlds interpretation, are there many worlds full of very lost birds? I don't think that's quite how it works. Instead, there are a relatively very tiny but non-zero number of worlds where the freezing of cryptochrome quantum states randomly failed in all avian magnetoreception, given the extensive use of homing pigeons by the Allied forces in World War II. My guess is that the Nazis would have won in all of these worlds. I think we just explained the premise of the man in the high castle. Nice one, physics.